Welcome back everyone, and today we got a new video, and today we're going to try to build an icosphere. I was not planning to make a video about this because it's actually not that complicated to make one. But when you try to make a UV texturing on it, that's when things become massively more complicated, and there really isn't a perfect solution for it. There's one person made a solution that works almost really good. By Michael Thiegessen. So even his solution is mostly perfect. Certain things don't work. I had to spend a lot of time researching, and thankfully, basically his blog about how to approach it and how to fix it, plus some information from the Unity community. They have like an example of how to create icospheres. And the funny thing is, building an icosphere, like this chunk of code is basically duplicated everywhere. Even the comments are duplicated half the time. So essentially, this is really just the vertices and the faces. That's the definition of the basic form of an icosphere. This is actually not even an icosphere at this point. This is the information on how to build an Icosahedron. It's a different shape. You create an icosphere from an icosahedron shape, which I'll show you what it looks like. This thing creates the UV values, but creates them with slightly different math compared to the other article. And mixing his fixes, but this math for UVs, and a couple of small other things, I was able to actually get it to work in WebGL and JavaScript. So this is kind of like, that's why I'm making the video, because the solution isn't really out there. There's one or two JavaScript samples. It doesn't work for me. I don't know if it's because the way I'm writing everything, or the way everything lays out, or it's just no one tests it and they just, I don't know. I really don't know why. Why for me it doesn't work, but I needed to do small things. Like I said, the math here is perfect. Like small things, like this one uses an cosine. I'm sorry, and in original math uses an arc sign instead of a cosine. So things like that, and there's like subtracting by 1, and this was adding pi, and the original math equation doesn't add pi at all. So there's a lot of little small things, which, like I said, the math from this community page does a better job mixing in with his fixes. This equation, which comes from Wikipedia, does not work for me with his fixes. So, like I said, this has required a lot of research and took several days for me to get right. So we're going to make a video about it, because I'm pretty sure there's someone out there who's going to want an icosphere that's easy, that it's mostly UV textured. And why do you want an icosphere as opposed to a polar sphere? Simply because an icosphere, you can manipulate a lot better with noise. So you can make weird shapes, and I think it's one of the shapes used for blobbiness type of effect. So if you have a ball that kind of that stretches and bounces, that's all done with an icosphere or other types of spheres, but definitely not a polar sphere, because you need all part of the sphere to be flexible, where a polar sphere is not. You have two polars, and all the vertices are kind of closer, or grouped together closer on the polar axis of the sphere. So that causes certain things. You can't distort it evenly throughout the entire sphere. With an icosphere, everything's built in triangles. There is a polar, but it's not as bad as a polar sphere. So you'll see how it is once we get into code. So we're going to be using a texture file, and we're going to use a new shader, very simple shader. I need to make a folder called just base shaders, just basic shaders we can use for testing. Like that's what I'm starting to do. So this is going to be a basic shader, which just handles rendering a texture. That's all it is. Very simple, nothing too complicated about it. Let me resize this window because we don't need it to be that big. You might be like, what the hell is that on the screen? I'll describe what it is in a minute. So, all right, so we're going to start off. And what we see on the screen is this part, just this chunk of code, which is a quad. which actually just creates a rectangle. That's all it really is. Let me just comment this out. Refresh. So that's it, just a rectangle. I think you could kind of use different dimensions if you want, but this is the dimensions that everyone uses to create an icosahedron. Now I can't even say it now. Icosahedron. How to make an icosahedron. So, an icosahedron is this kind of like shape that's made out of triangles. It's all triangles, big giant triangles that makes I guess the least amount of triangles you need to create something in a spherical form, and that's how we'll probably describe an icosahedron. It's a sphere with the least amount of triangles possible, essentially. And I was curious, how do you determine all the positions for these for these triangles? And the simple solution is, if you look around at the Wikipedia, it's really based on just 3 rectangles. It's all just 3 rectangles. So here's one rectangle. Like I said, it uses these dimensions, and I just clone it and rotate it into each own axis. So every single rectangle is basically a limited plane for each axis. So it's an X, Y, and Z axis, and that's how you kind of determine the positions of an icosahedron. I have to look on the screen because I can't say it. I need to look at the word. So if I click refresh, now you see the 3 rectangles, one for each plane. And the way you form the triangles is you go like, if you're looking at right here, you got that point, and that point. Those 3 points can form a triangle. Then you have this point, this point right here for that bottom one. Again, you can form a triangle. So if you go around the thing, you'll find all the points. You can kind of create this external triangle. And this is what forms an icosahedron. To really illustrate it, I have created a new geometry class. I'm going to step through it in a minute, but I just want to kind of show you what I'm talking about. So this is the starting point of a icosahedron. Like I said, that everyone's code starts off the same way with these sets of values. And like I said, these sets of values right here, these 3 sets, these actually define those 4 rectangles in 3D space. Where I just created it once and just rotated it. It's like I said, it's all the same thing. It's just the numbers are just swapped around. So ideally, you can there's a lot of different ways you can go about it. You can set one rectangle, then just do a bunch of rotations on it, and there's your new points. Or you can just hard code it, which is probably a lot easier and a lot less mathematically sound. One solution, one thing I always read about is that if you don't really need to compute something, just hard code it. Like if there's no reason to compute, there's no point in wasting CPU. So that's why a lot of things like this exist. Like here it normalizes. Like you should probably just normalize it and then just save it as a normalized value. So any form of computation, you can probably just compute it, use a computer to compute it, and then just hard code the values because it's never going to change. It's never going to change. Like especially for this, it's never going to change. So there's no reason for any level of computation that needs to be done. But this is how it's done completely for everyone else. It just makes it easier to code. Like I said, even though it normalizes it, I think we don't normalize it until like near the end because we don't need to normalize it till the very end, until we're ready to really use it as a sphere. So yeah, so like I said, I created a new geometry class, and I have a static object and with a function that just defines those values. And just to really just show it to you, if I go down here and just click geometry, that's all it is. And of course, I built my object to be super easy, as opposed to how it's built this way. Like I said, I built a class that's super easy to use, so I'm able to get everything done just with 2 function calls as opposed to I don't know, a lot of function calls. It was like 4 functions times 3, that's 12 function calls. So, but again, like I made a new, I'll show you the new geometry class in a little bit. like every time I do these new things, I have to create a new geometry class. I'm never happy with the last geometry class. So that's like an object that's always in flux. I'm always redoing. All right, so click refresh. Oops, I forgot to switch it to points. And I want to just have point values. Refresh. There we go. Now, as you can see, these points all line up with the 4 rectangles. So we would just connect the dots, make triangles. So, and the triangles already exist. These are the triangles right here. These are the faces. Sometimes when you see things called faces, they sometimes really just mean the triangles, because these are you create the faces that actually gets rendered. So you need to connect the dots to make the triangles, and those are what we're eventually going to see. So if I were to, let's see, I'm using that one. If I were to use, let's say, this one, as opposed to this one, which all the same, really. I really don't need to switch. And then switch over to our low poly Phong lighting, and then switch this back to its default, which is triangle. Click refresh. There is our Icosahedron. And this is, I guess, the bare minimum triangles you need to make a sphere. Very basic. So here's the geometry class. The geometry class I'm using is very simple. I'm creating something called Verts and Faces. We have done that kind of before. And the only big difference now is that normally I would start putting a lot of functionality into geometry, like to lerp things and to other things like extrude and rotate. I built a lot of that into geometry, like the last one, I think called geometry data, and it's always kind of like purposely built for what I'm doing for that specific video or that specific object. I decided to kind of step back and create something that's bare bones, something that's very simple, that allows me to kind of just contain data and manipulate data, not necessarily try to be the thing that handles everything. So in this new version, I created 3 classes. There's 4 classes in total. There is a geometry class, which just holds vertices and faces, and it just has certain functionality: how to add new vertices, and how to add new faces, how to clone it, and then how to kind of compile all the data into flat arrays that we can use for our GPU buffers. So our compile is very simple. I just use it in a smart way where I pass in the type, the size, and the sub, which is subcomponents of the vertex, or the vertex. So when we add a vert, we pass in everything, and I work it with all arguments, and we push it in, but we create a new class called Vertex. So we have a new class called Vertex that I never had before, which really is just the vec3. But it's a bare bones vec3, and I extended an array, so this way I can it's by default starts off at 3, but this vertex also creates 2 new values, UV and normal, which uses vec2 and vec3. Like, these are also new ones. I have a vec2 and a vec3. I have a vec3. I'm not sure of a vec2, but I made a new bare bones one. So I'm not, because I want something that's reusable and not held heavily to the math library. Like I said, I just want something that holds data. This is all this is hold data and lets me control data. Has nothing to do with mathematics or anything else. So like I said, that's why I wanted something very bare bones. So I have which is the exact same thing, just an array that's automatically predefined with XYZ, and I can do get and set with XYZ. So I can use it as an array, or I can use it as a struct, as like a vector object as well. And it's the exact same thing with a vector 2. It just has 2 components instead of 3. So, like I said, I'm building our geometry class with bare bones data management, and had no more data manipulation, just managing, just holding data. It doesn't manipulate the data whatsoever. So that's the new train of thought, new direction I'm going with fungi. It's like I really think about it in a different way. And if I remember, I haven't done too much work with Golang, but Golang kind of does things like that. You have structs of data, and then you have functions that manipulate that structs of data. And that's what I'm kind of going with. So I have these two functions called Geo Phase Centroid, which then uses that data and then manipulates the data. So it's like these functions aren't like part of that, because most of the time I don't need that. Maybe I don't need the phase centroid all the time, or I need to calculate the phase normal. It shouldn't be part of the geometry class. So I'm creating these side functions that uses the geo class and then manipulates the data for me, and then updates the geometry class with what I needed to do. So that's the new train of thought, and that's the direction I'm going with this video. So now that we have these objects explained to you, that's really all to it. And like I said, it's all very bare bones. And I think this collection, like this collection of 4, I think going forward would make things a lot easier. And I probably want to say a nod to 3GS, because for the longest time I've always wondered, they have a geometry class that has faces too, and I think also has edges. I'm like, why do you need faces and edges? I always work with verts. In the very beginning, I just used like a lot of flat arrays for everything. I didn't do arrays of objects and objects of objects. I never did things like that for WebGL, because I was able to do fine. But in this lesson, you start to realize, oh my God, I need faces. I might need edges. I need all this information. I need a lot of data that helps me determine how a shape is built. And this is the first video that we're really going to explore that. We need to know faces, and down the line we're going to need, and in faces we actually manipulate edges as well to create new faces, because now the magic of turning an isohedron into an icosphere, an icosahedron into an icosphere, is that we take this shape, we subdivide it, and then we normalize it. Now, subdividing it is actually a pretty forward step. So in true Sketchpunk form, I created ASCII art to kind of help me remember how things work. So as you can see, we have triangles. So with the faces, we know in our new geometry class, we know what the faces are. So we know what the triangle shapes are. So we know, and each face is just an array. Maybe I probably didn't explain it to you, that a face is just an array that contains the index of a vertex. And a vertex is an array that contains the 3 positions of that vertex, and it also contains the data, vertex attributes essentially, which are formed from vec2s and vec3s, like UVs, normals. I might eventually add joints back into geometry class, and joint weights, and like there's so many attributes you can have depending on what kind of mesh you're trying to manipulate. So like I said, we have a triangle. So once we have a triangle, which is A, B, C, and remember we have to form our triangles counterclockwise, because counterclockwise determines a face is the front face. If you do it clockwise, that means the back face, and we don't render back faces unless we say, hey, turn off culling, because we want to render the back face along with the front face. So as you can see, that's why it's called A, B, C in this order instead of A, B, C in this order. So it's counterclockwise. So when we subdivide a triangle, we have to know the 3 points of the triangle, and then we just find the edges, which is A, B, find the midpoint, and we find the midpoint of every single edge of the triangle, and then we reassemble all the points as new faces. So the new faces will be A, MA, MC. The next face would be B, MB, MA. Basically the midpoint for A, and midpoint for B, and midpoint for C, whatever. And then the next one would be C, MC, MB. And then the final triangle would be MA, MB, MC. Everything counterclockwise. So this creates a triangle, then we have a triangle here, then we have another triangle, then we have a center triangle. So every triangle, when you subdivide it, becomes 4 triangles. So in code, this is what it pretty much looks like. So we save our midpoints, we save the main points, and then we kind of, like I said, we just loop the faces. We get the index for all the points, right? We get the index for all the points of the triangle, and then we calculate the midpoints. We pass in the edges, basically. We tell it the geo object, and we have a cache. Now, why we have a point cache is because see how we have this triangle right here, right in the front. So once we calculate the midpoint, we're going to actually, when that midpoint gets added to our vertice list, and that midpoint gets the vertice, that point gets vertice, and then we kind of recreate our faces array with all the new faces. So the vertice list always stays the same, and we just append to it, and our faces get recreated because we're getting rid of one face and replacing it with 4 new faces. Now, that's this triangle. Now, when I start rendering this triangle and I subdivide that edge, it has the exact same edge as the first triangle I did. So the idea is that if we already created that vertice, we don't want to duplicate that vertice in the array. We want to try to keep them as unique as possible. So we want to reuse that vertice. So when I calculate the midpoint, I check to see, does that midpoint exist already in a cache? And if that midpoint already exists, give me its index in our vertice array. If it does not exist in a cache, create it in the vertice array and then give me its new index. And that's what this function called midpoint does. So if I go to midpoint, that's all it does. And it creates a key based on edge. So essentially, I make a key name, and I make sure it's in order by index. So it's index 1 and index 2. So if index 1 is less than index 2, I use index 1 as the starting point and index 2. And if it's not, I use index 2 as the starting and index 1. The reason why is that no matter which order you put it in, either this is the smallest number or this is the smallest number, I end up generating the exact same key name that I can use in our cache file or cache object. So this way, when I create it here, the midpoint I might end up putting the points backwards, but I don't want to accidentally, because the solution is, the reason why I'm doing it, and there's other examples that actually does the same thing, but I'm creating the keys differently as opposed to other people. One solution that's kind of neat, does this have it? I don't think so, not this one. They do it here. It's kind of neat, but we can't do it in JavaScript. Does this even subdivide? Yeah, I think it does. Yeah, the subdivide's here. Get midpoint. Let's get midpoint up. Probably get midpoints above. It does it here. There you go. The other solution, if you're like doing C++ or C# or Java, Golang or anything else, you can create a 64-bit integer, and then using basically the same idea, which one's the smallest one, build a 64-bit integer based on two 32-bit integers, and just make one integer value, and that could be your key. The reason why I'm using strings is because JavaScript doesn't have a 64-bit integer that I can use. It only has 32-bit integers. Sometimes in some languages it's called a long integer, or int64, depending on what language you're using. So since I can't do this the way you would normally, like, I guess if you do it if you use other languages, JavaScript, I have to use strings. So I use a string to determine, and sometimes it's not a good idea to start a key off, like if you use an object name with an actual numeric value. So that's why I put key underscore, because I know you can't like start variable names with numbers. You can't make a variable called 1x. I think you can't. I can't remember. So many languages I've worked with that I kind of forget. Some languages you can't start your variable names with a 1 or with a number. You have to start with a alphanumeric value. No, alpha value, not alphanumeric. Alpha. That's the whole point. It says you can't start with a numeric value. So we create a key, make sure that it's always in the right order. It's always the least to greatest of the integer of the indexes. And we just calculate the midpoint. So you just add the two x's, the two y's, the two z's, they add them together and divide by 2. And remember, multiplying by 0.5 is the same thing as dividing by 2. Since you're going to be doing this so many times, every little bit helps to optimize the speed. So that's how you calculate a midpoint. So once you have your midpoint, then you reassemble the triangle in the way I told you. Like, you know, A, M, A, M, C, which I here have T, A, M, A, M, C, whatever. And then this is the middle triangle in between it all. So basically you build the triangle all the way around and then the center. And you click, you say add it to faces, and you kind of create a new reference. And this way you can subdivide as many times as you want. I can say subdivide 3 or 4 times, and it keeps going in a loop. And at the very end, it replaces faces with the actual final version. So to start with, I start with the faces that exist. I create a new array called faces. I create that new face list based on the old face list, and then that new face list gets added to the reference of old face list, and then keep looping until we're done, and then add that to the Geo and call it a day. And I'm always returning this because I want to do chaining. So now that I explained it, now we got to do is call it subdivide triangle. If I click here, now here's our ISO. Now it doesn't look like anything has changed. If I were to switch this to points, can I do that? Actually, let me get rid of these guys. We don't need these anymore. Switch them to points. Every time I switch to the points, I got to go switch back into this other shader because it has the point sizes. So there's more points now. In case you don't believe me, since I did all this other changes, take away subdivision, refresh, less points. And you can say, so I can say subdivide even more, to subdivide it twice. So every triangle gets subdivided, then the second loop, it takes all the new triangles and subdivides them even further. Now there's even more points. Now it's still the shape of a Icosahedron. It's still that shape. Now to make it into an icosphere, you have to sphere it. So let me just do this once and switch everything. I'll just leave it like that for now. Click refresh. And you know what? Let me switch it back into Fung lighting and triangle rendering. Refresh. So like I said, we subdivided, but still an icosahedron. So next thing we're going to do is say, turn all the points into a sphere. Spherize it. Spherize it? I don't know if there's a term for it. I tried looking it up. And now you can see, if I undo it again, there's our hydro something, whatever. And spherize it, and boom. Now it's more of a sphere with a bunch of triangles. As you see by using our lighting shader, we can see all the triangles. And in this function, you can pass in the radius. So if I want to make that a little bit bigger, just pass in 2, and now it's a nice bigger value. You want to keep it small, you can make it small. There you go. So to spherize an object, how do you do that? Well, it's actually pretty simple. It's a very simple solution. Simple solution is you normalize every single vertex to the origin. So it's just normalize it. That's all you got to do. And this is all I really am doing. I'm calculating the magnitude of the vertex based on origin, because everything is at origin anyway. It's local space. I divide by 1, and the only reason why I'm dividing by 1 is because I want to get rid of division. So if you want to take away division, you divide one divided by that, and you can turn that division value into a multiplication value. So V has our vertex data, and I'd say X times D, as opposed to X divided by D. Like I said, if I get rid of this, it's divided by D. But like I said, I normalize it, and I save it to normals. Like, since I'm normalizing it, save it into my normal values. Save myself time from normalizing it later, because making a sphere, every point is big. To spheralize it, and like I said, it's a really bad term because I don't think it exists. It's not a real term. To sphere it, you normalize every vector, which is the normal value. So like I said, I'm just save time, just double it, save it. Since I'm adding a radius, I can just take that vertex and just say multiply radius. So I can keep my normal value unchanged and still use my radius all at the same time. So that's how I built this function, to be able to turn everything into a sphere and then keep its normal direction. So this way it can use those normal directions in lighting for our shaders in the future. So, and the same idea can be done for a cube. You can actually turn a cube into a sphere. You take a cube, you subdivide the cube, and exact same way. Every cube is defined by 6 quads, and every quad is divided by 2 triangles. So you subdivide every single triangle, and then spherize it, and you turn basically a cube into a sphere. And it's a different type of sphere too. That's there's another term for it, but it's a completely different type of sphere that's a little bit easier to map textures to. So and it allows you to create like sectors, because you have the left, top, bottom sectors. It's one of those shapes that I think that kind of circle is, I think, sometimes used to create planets, because you have sections. Everything is really in a cube form, but everything got converted into a sphere, but everything is still lined up as a cube, essentially. But this is an icosphere, so everything is perfectly circular for the most part. And there, like I said, there is a polar. Here's a north pole, and here's a south pole. And you can just subdivide as much as you want. So I can say 2, and the circle should be more defined. See, now it's a lot more defined. It's more spherical. You can go up to 3. You can go as much as you want. It doesn't really matter. It just becomes more and more defined. This is kind of starting to look like a golf club. So let's go back to 1. So here we go. We have basically now our starting point of a sphere. We convert an icosahedron into an icosphere. Now the next thing is, now this part is, everything is easy. This is no big deal. Everything we've done so far, you can find tons and tons of articles about. It really is no big deal. I probably shouldn't have wasted so much time on it. And to prove my point, here's my list of references that I read to actually study this subject. Lots and lots of things. There's actually some really good stuff in here. But this is a lot of all the articles I've read, and all the main things that have some good small bits and pieces that I use to help me understand how some of this works. So now becomes the complicated step that actually everyone has problems with, and there's not really enough information about. It's the UV mapping of an icosphere. So really, it's really simple. All you do is go through all the vertices, and you grab the normal direction, and you apply some math using that normal direction. That's why I said, when I did the 2 sphere, even though I want to set a radius, let me save the normal, because I can use that later. I can use it for lighting, but in this instance, to calculate the UV normals of a sphere, you need that normal value. So the UV, to create that UV values. And this is the original math that comes from Unity, this Unity community page, as opposed to this math, which comes from the Wikipedia page. Like I said, the math is different. This one uses a tangent to x and z, and this one uses z and x backwards. So that's why I was having a lot of issues. But it's actually doing adding a pi to it, and then it's multiplying by half pi. which actually is divide by half pi actually, where this one divides by pi 2. That's probably because it's adding pi here, so this way you can take away another half pi there. I don't know. I don't understand how the math works because I really sucks at this high level math. But like I said, this math actually works as opposed to the original article that uses that equation. Like, I don't know how he got his to work, but once I wrote all the code, nothing really worked correctly. The textures were inverted. They were like not coming out right correctly. It took me like days until I found this Unity page, and I saw, well, the math is different. It's done differently. But you know what? I trust Unity because Unity is a gaming engine, and I'm pretty sure this works. So this works. So like I said, this is the original, and this is me doing a little bit of optimization, replacing the vision with certain things like this part here, which is you have pi divided by 2, which is half pi, but you're dividing by half pi, so I'm multiplying that to cut it in half, and then inverting it. That's what I call an inverted half pi. So this way I can do multiplication, same thing, and just inverted pi and inverted half pi. So, like I said, this also uses arc cosine, and this one uses arc sine with y, yeah, but it doesn't add pi to it. It just divides by pi. This one adds pi to it, then divides by pi, and then subtracts by 1. Again, like I said, it's the only way I got it to work, man. I'm not a mathematician, so I just got to try every equation until something kind of works. So that's how you define the UV values. So here's the U values. If I click refresh, you won't notice a difference. But you will notice the difference if I apply a texture to it. So we're going to use our texture UV material, and we're going to use this VEO, excuse me, that brings everything in. So it brings in our vertex array, our UV array, and our face array. And like I said, I think I showed you the equation. It's like the math, the function is so simple. It's nothing. So if I click refresh, and there we go. Now, like I said, the texture was backwards. Like the 1 would appear here. It would be like 0, 1, and like things were just really bad. Now, here's the problem. The Unity page stops here. And most articles or most things kind of really stops here. Like there is no easy fix for this. That's why I said there's only one article that explains kind of how to fix it. So the idea, like his idea was, first you got to find the issue is that the way he's you're better off really reading the article. I'll see if I can summarize it. Is that between the triangles, it's trying to actually render the entire texture within just that one triangle. He says that the UVs are essentially backwards in a certain way, and that's why they render in a very bad way. He says like if you look at it in terms of normals, it's pointing in the inverse direction where it's pointing in the back face, and that's why everything's kind of screwy, because you have certain things going in the right direction and you have other edges going in the wrong direction, and everything gets really screwy. So his solution is basically find the triangles that are messed up, essentially. So this is the next function: fix wrapped UVs. So I'm going to do this. Now, there's another problem I found in the article where originally in his equation of how to determine that, and the way he determines it is the same way you determine a normal. So like when you do a normal, you take let's see if I can. Like the way you determine normal direction, like for a quad, you remember you take that one point, you calculate the length vector of like that one side, and then you calculate the length of that side, and then you do a cross product. And if you do it the cross product, A and B, like in the right order, like basically it's BA minus CA, and the final equation is BA minus CA cross of CA minus A. So like if that's A, down is B, and over there is C. So the distance of the vector length of this edge crossed by this edge should give you a normal direction that faces outward, like towards you, toward the front face. Now the problem is if it's pointing inward in an inverse direction, then that UV value is wrong. But to do he says the Z has to equal less than 0. But if I use the new math that actually maps the UVs correctly to my sphere, that's wrong. So but I just tried out making it greater, and then actually figured out it works. So his stuff does work as long as you go in the opposite direction based on the math from the Unity page. And I was able to kind of just be able to visually see it finding the triangles. I probably haven't commented it out yet. Yep, fix UV. So like the first step in that function, you have to find out which triangles are broken. And he's right. See, I pointed every single triangle that's broken. So I have everything pointed in color. So RGB. So I know that's A, that's B, and that's C. That's the order of the triangle. Now the problem is that you can't see the distortion anymore. Let me go back here and just say continue regardless. I'm not going to fix anything. So there you go. Now you can see how it was before. So this is what it looked like before, and this chunk of code right here, like it's really not a lot. It's because I'm doing a lot of commenting to really illustrate. And that's probably one of the best things about the sample I'm giving everybody. It has like tons of comments because it's kind of a complicated subject, and I try to explain to it as much as I possibly can using points that, okay, this information comes from here, but it doesn't work in this context for some reason because the math doesn't, whatever. Like I'm trying to tell you. But like I said, it works. It finds the triangles that are broken. So now that we know which triangles are broken, we have to check to see if it's in the positive direction, not negative. I do check if it's negative and continue. That means if the broken triangles are the ones that's greater than 0, that means the triangles that are not broken are less than or equal to 0. So that's why I say just continue. I don't need to fix anything if the triangles are not broken. So I can leave that alone for now. Now, the way this works is that it does some math, and like I said, I really can't explain it too well because I'm not a mathematician. But there's a magic trick to it where it duplicates of one of the vertices, and whatever vertice that's like has this value less than 0.25, like a UVX value less than 2.5, on the broken, like any vertice that's broken that has a UV value less than 0.25, you just add 1 to it. And the magic trick is that the texture has to be loaded in as a wrap. So if you have your textures loaded in as clamping, that means you can't go past 1, you can't get under 0. This way you can. So even though the value might be, let's say, 0.25, I change it to 1.25, and it kind of just ends up wrapping around to the other side of the texture. Which 1.25 should still go in the same direction? I don't know. But it just wraps around. But like I said, it fixes it. And then so I clone that vertice. I do the same kind of cache effect like that we were doing before. So it's the same idea. In this one I called used, but it's just caching the new vertice. And if that new vertice exists, reuse it. If it does not exist, create it. And then that face value, that point on the face, replace it with the new vertice that I created. If the vertice already exists, just use it. Just give me that position. And for this one, I'm using a map object as opposed to using an object where I did in the other one. Like every function, I'm kind of playing around trying different things. This is ES6 new functionality using the map function. It's really just a dictionary. It's a key value pair object. In case you're new to that, if you don't using ES6 stuff yet, I'm starting to do that. And that's really the gist of it. Like I said, you just find this. First, you find the broken triangles. Find out which point of the triangle is less than that specific value. I guess, I don't know. Like I said, he explains it better than I can ever. And then just add 1 to it and make sure you don't duplicate that vertice that got modified. And all you modify is the UV value. So I clone the entire vertice, and I just change the UV value. On the X plane. Like I said, if I refresh, those triangles that are marked are fixed, and now we get the texture. Now it's completely around. It ends at 0.9 and starts back up again at 1.0. Now the only thing left is the polars, and the thing is, he tried to fix the poles as much as he can, and he did the best he could. I'm trying to say, yeah, it's not perfect, and I have the same issue because I'm using his algorithms basically, but it's better than what's there. Like this looks like really bad, so you can fix this. And the solution really is the same idea how he fixed the seam, where you duplicate vertices. So what he does is finds all the triangles in the polar and then duplicates the polar UV, the polar vertice, and gives it a an X. Gives you like an X or a Y. I think it's an X. An X UV value that's an average between the 2 points that it's connected to. So like those 2 points connect to a new one, and so forth and so forth. And that's really all you have to do for that. So if I get rid of this. So the final step is we need to fix the polars. Now, God, I'm keep putting the wrong button. Now, the biggest issue is that I had to deviate from his because for some reason he says the way he creates the icosphere, the polar coordinate is always in the A position of every single face. That's not true for me. Even though I used the same thing as a JavaScript function, like I said, I use the exact same list of vertices and faces as everyone else, and I'm basically subdividing the triangles the exact same way, and then creating the new triangles in the exact same order as everyone else. I still don't get that result. So to fix that problem, I had to, like I said, I had to deviate a little bit. So let's see. So I have here's a function kind of based on his fix UV pole. God, I keep putting the wrong button. Yeah, this sucks, but I created something called find and fix poles. So let me see if I can just see how it works. It's not a function. Oh, because I accidentally deleted the name. So oh, I didn't have the points. Oh, damn. Oh well. So the first thing is I need to find the poles, and like I said, he didn't have to worry. The way he did it is that he loops through the entire actually when most people do, because I don't know what I did wrong, that my poles don't show up on the A position, like the first vertice of a face. But if you guys can find why that's wrong, that'd be great. But since I'm not, I had to figure out how to find the poles. So to find the poles is that it is a pole. So the pole of a circle is always going to be the greatest or smallest point on the y-axis. So if that's the case, so I just loop their entire vertices and just figure out which one is the smallest and the minimest, the smallest and the largest. And that's all this loop does, is just find all the vertices. And then I have it displaying. So there's the North Pole and there's the South Pole. So once I've found where the North and the South Poles are, I loop through the faces and try to find anything that's in the B and C position. If any face has the pole in the B or C position, I just swap things around where everything is in the right order. Where the pole is at A, then everything lines up correctly with B and C. So that's all this thing is. Just this very long, but I'm just swapping things around. So if like I said, if X equals the North Pole, this is how you fix the North Pole. If this is the minimum, this is how you fix the South Pole. South Pole, North Pole fixes the exact same way. That's why I kind of put them together. So like if the problem is in the B position, North and South Pole are fixed the exact same way. If it's in the C position or the Z, because it's a vector 3, you fix it the exact same way. So Imax becomes the first position, and everything gets swapped out in the right position. You got to keep everything in the right order, because the order of operations is very important. Because if I were to do this over here, that means I updated 1, and that one goes into 2. So you got to make sure everything's in the right order, so you don't override something by accident. Because I did that a couple of times, and things just got wacky until I got the order. I know how to create the order, but I made a mistake here and there, and when I figured out the problem, I know it was the order of operations. So I just swapped the order of operations, and everything got just done right. So that's where I'm just fixing the faces and making sure that the pole is the first, because that makes things super easy. Because once that's fixed, I can then fix the poles. And like I said, the idea is that you so I loop through. So the idea is you loop through all the faces yet again, and I'm just checking to see if the pole, which I return min and max, is there. If it is there, or if the face is not part of the pole of the sphere, continue. If it is a triangle that's connected to the pole, when we get the indexes, we are going to clone the pole. We're going to calculate the new UV value for the pole, and then we update the face with the new vertice. And that's it. So, like I said, you just create a new vertice and then just update the face with the new vertice, and that new vertice has the new UV value. That makes things a little bit better. So click Save, refresh, and now the poles are better, but not perfect. And like I said, I have the same problem that he did, and that's where he kind of just left off. And I couldn't find any other solution that continued this research on how to improve the UV mappings of an icosphere. So that's why I kind of made a video, because there's really not a lot of information out there. Everything looks kind of crappy. It's because of the divisions. So you might look, it's like, oh, the lines are a little bumpy. That's because of the resolution of the geometry. So if I were to subdivide this to 2, click Save, refresh. Now it's more sphere. You only start noticing the problems when you get into the pole area. But let's say if I do a subdivision of 5, which creates a lot of vertices, everything is a lot more smoother. And as you can see, the pole is actually really good, because I localized. Because the triangles that connect the pole are really, really tiny, and so you can kind of get most of it pretty good. So it really depends on how many levels of subdivisions you do. I think 3 might be good. 4 is good. I think 3 might be like the bare minimum to get a pretty good texture to line up. Yeah, somewhere between 3 and 4. 4 is perfect. Like if you want that final line to be perfect, you have to subdivide by 4 times. But if you really care about your vertice count, maybe do that by 3. Because you got to remember, every triangle that you subdivide becomes 4. So every time you do a subdivision, you make it 4 times bigger. There's 4 times more vertices. Or actually, there's more. Ideally, it becomes 4 times bigger. So there you go. So if I'm going to just subdivide it once, and for funds, like I said, I wanted to play with the geometry class and creating new functions. Like just have functions that can use the geometry class. So I have one here called Geo Phase Centroid, which takes face information. So I basically give it my geo class and tell me the index of the face, and it outputs the values of a vec3. So what it does, it calculates the center point of a triangle face. So this way I can determine the center point of a triangle. You might say, why is that important? Well, if I want to do some fancy animations with triangles, let's say if I want to build the isosphere with every triangle as an individual, I can then get the centroid. By knowing the centroid position of every triangle and the normal direction of the face, I can actually animate of every triangle to move away from the sphere, but still in a spherical way. So I can do some really funky functions where I can have triangles slowly moving away and then reforming back. So maybe I'll make a video like that. If there's like a lot of people that want to see that animation, please just rate comments. If I get like maybe 5 people saying, I want a quick video of how to make that kind of animation, I'll give it a go. If not, I'm not going to bother. But like I said, this function will help me determine the centroid of that sphere. And like I said, I wanted to know how to calculate the normal direction of the face, not just the normal direction of the sphere. So like for that specific animation, you replace the normal direction of every point of the vertice with the actual face normal and not the normal of the actual vertice, because you want to move all the triangles in the same direction. So I don't think you need the centroid. No, I think if you just have the normal direction by itself, you can get the animation just fine. But if I want to move things, like if I want the triangles to move like on a sine wave or something, or do some kind of curvature, I need the entire face to move in the same direction. I move the centroid and then move the other vertices in the same direction. So if I remember correctly, to do that kind of animation, you do need the centroid if you want to do some really funky animation. But if you just want to move it away from the sphere center, you can just use the normal direction, the face direction of the face. And to really see it work, I have the final function, which is called Debug Normal Face, which all it does is calculate the central point of every triangle. And you probably can't tell, but if I were to just switch over to Fong lighting, now you can kind of see I put, and I use debug lines, I put a center point and then your normal direction of every face. And there you go. I was able to debug and make sure I'm actually calculating things correctly. And the simple function at the end, debug face normals. Like I said, it's very simple. Yeah, so it's normal, that, and then I just calculate the endpoint of the lines, because the centroid is going to be the start of the line, and by taking the normal direction times a certain radius plus that centroid, I get the second point of the line that's away in that direction. So like I said, ideally you can make those 3 points of a triangle move in that direction by just calculating the face normals. So there you go. We learned what a icosahedron is. It's just 3 rectangles, 1 in each axis. We learned how to subdivide it to start converting an icosahedron into an icosphere. and we learned how to simply calculate the UV coordinates for it, and then how to fix the UV coordinates to get the UVs to actually map mostly good. You know, like I said, like I would say like 90% good. It's not perfect, but it's pretty good. And the higher the resolution of your sphere, the less of the distortion you'll see, because all the distortion happens at the poles of the sphere. And yeah, that's it. There you go, Icosphere. Fun, fun, fun. So that's it. I guess I'll see you guys in the next video, and see ya. Bye. Oh yeah, I forget the usual BS. Like and subscribe. I think I don't know if I mentioned that because I'm in a hurry. And yeah, just like and subscribe. I almost got 1,000, so I might start getting new YouTube features once I think I hit 1,000. Or is it 2,000 subscribers? But I don't know. I'm almost there, and I really appreciate. I thank you everyone for subscribing. Like I said, I get new features, and I finally will get back on the ad sense. You know, I can get money on ads again, I guess, which, you know, I get like, you know, $2 a month or something. So yeah, I wasn't planning to make a video about icospheres, but this whole UV thing said that I maybe really should make a video in case people need a good sample of code from start to finish of how to build one, and having a geometry class and vector class and all the math and everything that perfectly works, and you can has like debug code so you can kind of see everything as you go. Like I said, like I had tons of debug code in there, so you can visually see where everything is happening. Like I showed you how you can see where the seams were having the problem. So, yeah, again, see you guys in the next video. I have no clue what the next one is, but hope you guys like this one.